Hello, hello, hello. Nice. Cool, yeah. Hi, I'm Dominik. I'm from Polygon. And today I'm here to talk about Polygon Maiden. It's one of our zero-knowledge rollups, but it's quite different to the others. But I don't want to shield the product. I actually want to talk about the problem that we're trying to solve. And actually, we want to combine public and private state because we think that scales better. Basically, our hypothesis is that privacy scales better. And this is different to what we have in blockchains today. Basically, I want to talk about state, and probably you all know what state is. But state describes the specific condition of something. Let's say of an account, or of the whole rollup, or of a whole blockchain. But verifying a block in a blockchain, at least traditionally, requires public state, right? So I need to have access to all the state to be able to recompute or to be able to execute the transactions. And public state, unfortunately, doesn't scale. If we want to continue, or if we want to really onboard 1 billion users somewhere in the future, then it will not scale if everyone knows everything and if everyone always recomputes everything. So that most likely will not scale. Zero knowledge now allows us to verify something without knowing the state. That's the magic of zero knowledge, right? So with zero knowledge, I can verify without being transparent. And some state must be public because we want to interact with public state. Most of the state can stay private. And I want to talk about our solution, but I try not to shill our product, so let's talk about the problem. As I said, state describes a particular condition. Let's say we have an account here. This account has 5 Matic and 2 ETH, and it can have these balances. It has a nonce. Accounts can have code or like a special storage, and this storage can have certain values in storage slots. And blockchains, they use this state and store it in trees, like in multi-partition trees in Ethereum, but it can be anything else. They try to make it efficient, but basically state is stored in trees. We can also think about how Bitcoin stores state, like in an UTXO database somehow. But this state, basically the specific condition of everything that the blockchain defines, must be stored somewhere. And the problem is, as I said, like the block producer executes all transactions in a block, and then all the other nodes, they re-execute the transactions in a block. And re-executing means changing, like applying the same state changes. Every transaction is a state change, as you know. And so everyone re-executes everything. And then that means all nodes need to know the same tree or the same state. And so now the question is this possible? So let's assume we would have 5 billion accounts and 25K TPS. Is that realistic soon? I don't know. But like it would be if we want to follow like what we really want to achieve, right? 25,000 TPS is around what NASDAQ is doing. And I always say like that would be the best blockchain use case to put NASDAQ on a blockchain. It totally makes sense. But then we need to do 25K TPS, 5 billion accounts. Okay, let's assume lots of devices are also on the blockchain. But what does it mean? So for state, if we would say 400 bytes per account, we need 2 terabytes to store state. That might be realistic. But if every account has 100 assets or some complex NFTs, or maybe even if every account is a smart contract having custom code, then it's not unrealistic to have 4,000 bytes per account, which means we need 20 terabyte. That doesn't sound unrealistic. 20 terabyte could be even in a small SD chip. The question is, how quickly can you access it? If you have 20 terabyte and you need to access 25K TPS state changes. Some state changes might be more complex. That's a question, but it's still not unrealistic. There's a cool talk of from Peter, from Geeth, about the physical limits of scalability, and it's exactly about that. How fast can you, in theory, access state on a hard drive? So it is realistic, but it will be hard. But the bigger problem is bandwidth, actually. So let's assume we want to have these 5 billion accounts, 25K TPS, and we assume that we have 100 bytes per transaction. And that would be a simple ETH transaction, right? I send you 5 Ether, and then we already need 2.4 megabytes per second. Do you know the current bandwidth of Ethereum? So after proto-dunk sharding, this is what we all are waiting for. It's 32 kilobytes per second. After dunk sharding, which comes in 4 years, roundabout, like it's Ethereum timeline, we have 1.3 megabyte per second. And now, if we assume we have more complex transactions, this is the current average, 600 bytes per transactions, we already need 14 megabytes per second. Right? So because every one, like this is bandwidth means how available or how fast is the data available on my blockchain, and this is maybe with the near approach, like when we have 16 megabytes, what they said per second, but at least on Ethereum itself, it doesn't scale, and the problem is not rollups. Like even all rollups together, like they need to store the state somewhere. And they need to, like the bandwidth means also in call data, like we need to somehow publish the state. And the rollup can publish, signed signatures for optimistic rollups. Maybe you can compress the data for zero knowledge rollups a bit and publish state diffs, but you will not come below that number pretty much. Because somehow people need to know what's happening. And the same for execution. So we assume that 100K gas per transaction, then we need 2 billion gas per second. This is like super far away from where we are at the moment. But like if we have 300K gas per transaction, we need 6 billion gas per second. And at the moment, how much is it? 30 million gas every 12 seconds, right? So I should have done this computation before. not so much. Let's say, is it? It should be something like 4 million gas per second. Let's say an estimate. Okay. Exactly. So meaning that if we want to reach these numbers, we cannot continue with only public state. And that's. The layout is a bit off. So basically what we suggest, and not only we suggest, but like the whole ecosystem is moving, is that we can do state transitions with zero knowledge. And that looks like this in a super simplified format. But here we have Paul, for example, he did something, here's the proof, and everyone says, okay, that's correct. But we don't really know what he did. Basically, what Paul does is he creates a client-side proof. Like he proves his own state transition and only sends the proof to the network. No one needs access to his data. We use the zero knowledge property of the zero knowledge proof, and that means that when users create their own zero knowledge proofs, we get cool properties. For example, privacy, which is quite nice, and actually it's something that is lacking in our ecosystem so far. But we also get high throughput. And we even get, when users create their own zero knowledge proofs, we get even higher throughput the more private the people use it. This is because, like very simply put, but it's way easier for a network if you check the correctness of a polynomial, like in a stack proof, for example, which is super small, than recomputing and keeping the state. And you can create these zero knowledge proofs in parallel, so you get vastly better throughput if people use the rollup and the blockchain privately. That's the thesis. Okay. So, but the problem is, here, for example, we see Alice's account that can be private, so no one needs to know how much money Alice has. That's good for Alice and maybe good for us. But the thing is, there is also some state on a blockchain that we want to be public. Think about an AMM, and it has a fixed FX rate, and that is cool. If this state is public, then everyone sees it, can access it, and so we can have some state public and some state private, and this is our architecture, basically, that people can decide which state they want to have public, and but the rest can be private, and state transitions can be done with clients and proofs. I quickly go over the architecture, and then I just want to check how much time I have. I have until, it's good? Can you tell me 5 minutes before? Now it's 5 minutes? Okay, so, okay, then I got a good feeling. Okay, basically the technical architecture is based around the actor model. But the core idea is, in the actor model, that actors are state machines with inboxes. And these actors are responsible for their own state. Right, so this is the core idea of the actor model. Basically, think of a high-performance database, and like there are small actors in this database, and they send each other messages, and then they get a message, change their state according to some rules, or they don't change their state, it's up to them, and then they send out other messages to other actors. And this is how we design Maiden. These actors, they communicate via message passing, and these messages are produced and consumed asynchronously. And in Maiden, we have accounts, which are our actors. You can think of Ethereum accounts. They can own assets, and they have code. And we have little nodes. And these actors, they send nodes to each other. And accounts and nodes can carry assets. And yeah, the core idea is basically how we change the notion of a transaction. And then I stop. But what we want is that an actor or an account or a user can basically prove its own state transition, right? And so we defined a transaction such that a transaction is always executed against a single account. Think about, like, it's different to Ethereum, right? The Ethereum transaction always involves at least 2 accounts. Alice sends something to Bob, or Alice does some ERC20 and changes 35 different accounts, but it's at least 2. And in Maiden, it's always 1. And because it's always 1, we need 2 transactions to transfer an asset from one account to another, as I will show. But because every transaction includes only 1 account, this account can prove its own state transition. It doesn't need data or knowledge of the state of the other account to be able to create a valid proof. So in that case, account 1 has 10 Matic, and in the first transaction it would create a node. It's like in the Bitcoin system, we have a UTXO tree, and then so then now there's a node carrying these 3 Matic, and at a later point in time, account 2 consumes this node and now owns 3 Matic. And yeah, this is how it looks like. We have these tiny accounts, and they send nodes to each other. And every time a node appears or disappears, it is a transaction. And every transaction has always a zero knowledge proof, either done by the user himself in a mobile phone or by the network. But that's for another presentation. But every transaction always has a zero knowledge proof. And that means that we can even parallelize, like we have parallel transactions, we can parallelize the proof creation, because I only need to know my state, and then I can just create my proof, and Alice can do the same on her machine at the same time. I think the 5 minutes are over, is that correct? 1 minute?
There's 5 more questions.
Okay. Yeah, as I said, basically every transaction has always a proof, and then we just we basically recursively batch these proofs together. But another way to explain it, another way to think about it, every account in Maiden, like these little state machines, basically you can think about them as their own zero knowledge rollup in a zero-knowledge rollup. Right, so basically what you can do, and this is how they store their state themselves, basically what the network knows of an account, if you want, is only a hash, right? And then this hash changes, and together with this like state change, or together with this state root, there comes a zero-knowledge proof from this user, and the network can accept it or not, but if it's a correct proof, the network will accept it. And this is exactly how a zero-knowledge rollup looks from the perspective of Ethereum, right? What Ethereum knows is the state root of the rollup, it gets a new proof, a new state root together with a proof, and then it changes the state root. And so this is exactly how accounts would look like in the private state mode in Maiden to the network itself. And the same way as a zero-knowledge rollup scales Ethereum, not enough, but it does scale Ethereum. The same way, every account scales Maiden in the network, right? So this is basically the mental model. Yeah, and then we have private and network execution, and we have basically public state. That's the other part of the presentation, but public state actually works like on Ethereum or on any other blockchain. So there is the whole data being stored of an account on the blockchain, and everyone can see it, and then we know what the current exchange rate is of something. Yeah, like this is actually a completely new approach, but it's just like we take it a step further with the zero-knowledge stuff. So basically now we don't have a centralized prover that creates a proof for all the participants in the network. Now every user needs to do the work. That's why it's faster and less resource intense for the network. That's why it scales better. But it's also way more researchy, so to say. So we haven't had a single transaction yet. We hopefully have our first end-to-end integration test from an Alice to a Bob this year, where Alice creates a zero-knowledge proof at home. Yeah, like it's super cool to work in this project, but it is, yeah, researchy, and hopefully we can get it out next week. Not next week, next year. Next year. Next week would be nice. Next year. And it opens up for new use cases. So with this, you can build stuff that you cannot build on an EVM, which is quite nice. But I also like to say the disadvantage is like usability lags, obviously. So like people need to know Rust. We write our smart contracts in Rust, which could be okay, but also we have like lots of new concepts, and we try to abstract a lot away from the developer then at the end. But yeah, I think this will be a long way until people really have an easy time developing there. But yeah, I think that's it. So this is how we try to solve the state problem. Can I close that somewhere? We can make this. Are there any questions?
See, this is very fantastic. One question. The nodes are public, no? The contents of the nodes?
That depends. Like accounts and nodes both have two modes, and nodes can be public or private.
But if I'm sending you the node,
yeah,
if I don't make it public, there's no way for you to process that.
It depends. Like public means if you put the data on the blockchain.
Yeah.
Exactly. Like you could also send me the data in a side channel or over WhatsApp. Like to be able to process or to consume the node, you need to be able to execute a transaction and create a proof for it. For that, you need the contents of a node. And the contents of a node you can get over a side channel or off-chain or, yeah.
Quick question on just the experience of this. So do I have to manage my own nodes as well?
That depends. Yes and no. So, like, if you choose to stay private, then obviously it's the cheapest option. Mm-hmm. Then, like, what we aim to do is we aim to build a wallet together with a partner, such that the data can be encrypted, and you can store the encrypted data on Google Cloud or on any other cloud provider.
But I'm still managing it.
Yes. Then you manage it. However, you can also instead of putting public data on the blockchain, you can encrypt the data and put it on the blockchain, so you know it's stored there, and then you only need to manage your decryption key, right? But then basically you know the data is there, so you would have these three options actually. Yeah, but that's a problem indeed. So you are responsible for your own data because the blockchain doesn't store it for you. Yeah, exactly.
Just a question: is this when one account sends node to another account, can it send it to a smart contract? And does that basically transition into two transactions, or just because can the smart contract receive a node or not?
Yes, so like that.
And how does that work?
Yes, like every account is a smart contract, and I as a user will use an account, but also a super complex smart contract, or like Uniswap could also be an account. And the protocol is the same. So if I send something to Uniswap to swap, I have a slide for this. I just need to. Then basically I create a node in the first transaction, and the Uniswap contract waits, for example, here, that we have a Uniswap contract in two accounts. So I create a transaction with a node and say I want to change 10 ETH to whatever price you give me in DAI, and another account wants to change Matic to USDC. And so asynchronously they create nodes and send it to Uni. Uni could every second or every 10 seconds or like in a certain interval consume all the nodes together. Like in one transaction you can consume up to 5,000 nodes and sequence them. And then Uni would consume the node, and in consuming the node, the Uniswap contract needs to execute a node script. And this node script basically is Turing complete, so you can write anything, but it needs to be executed. And you would write in node 1, in the node script, you would say, please consume these 10 Ether, but send me 10,000 Matic. And then Uni needs to, because Uni wants to consume the node, needs to send out another node with this like receiver with 10,000 Matic. Does that answer the question?
But who would initiate that transaction?
In that case, account 1 would initiate the transaction and would say, I want to swap at Uniswap, and therefore create a node. And this transaction 3 here, like the Uniswap transaction.
But who initiates the Uniswap transaction?
That could be the operator of the Uniswap thing, or it could be the network operator. Like if you send a public transaction, then you have, just like in other rollups, like a sequencer or a decentralized set of sequencers. We just call them operators, but they execute public transactions. So then it would be exactly the same as in a normal zero-knowledge rollup. So where the transaction gets executed by the sequencer. Or yeah.
But in this case, it means that the Uniswap state has to be fully public, right? So what we say is that some contracts like Uniswap have a fully public state, and then sequencers can execute them.
Yes.
Okay.
Like some contracts have a fully public state. Like this is basically what we have. I want to make that easier actually, but like you can have a network execution or local execution. That just means who creates the zero-knowledge proof. And the data can be on-chain or off-chain. But in the example of the Uniswap, you would have public transactions. So the state or the data is completely on-chain. Everyone can see it. Also the network operator who executes the transaction, meaning that it creates the zero-knowledge proof. Yeah.
I have a question about the private transactions. So if you send like $1 from A account to B account, and the state transition remains zero knowledge, which means that the transition only results in root hash changes for both A accounts and B account. But to achieve that, you need both A and B to provide off-chain ZK proof. Is that right?
Yes and no. Like if both, like basically, A and B can both decide on their own whether they want to have a private transaction or a public transaction. So A could say, I want to send B $1, but I don't want that anyone knows that I sent B $1, so he does a completely private transaction and all his data is private. But B could say, I really don't care, or I'm rich as fuck, and he does a public transaction. And so, like the node, yeah, it depends. Like basically, it's independent. Like these both transactions are decisions of the receiver or sender, because a transaction always includes only one account.
So the transaction only includes only one account.
Exactly, like that's the core paradigm of Maiden. A transaction always includes only one account. Basically, a transaction is defined as the state transition of one account at state 1 to state 2. This is a transaction, and by doing so, like it consumes several nodes and it produces several nodes, but it changes the state of an account. This is a transaction, but only a single account.
But let's say if I send $1 from A to B and only B account is committed on chain, which means the root hash is changed, but the A account root hash doesn't change and spent to another one. Is there the double spend problem, or that's not the case?
Not sure if I completely, but we can maybe do this example and then see if I answer the question. So account 1 could send something to account 2, right? So account 1 creates a node, and that node has 3 matic, and this is transaction 1. So after transaction 1, the hash of account 1, everything the blockchain has seen, that changed, right? So now we have a change in the account hash of 1, but nothing else happened. And we have a new node in the node database. And this can either only be a hash or it can be the full node data.
Yeah.
But nothing in account 2 changed. And then we have account 2 who can consume this node. And this is a second transaction. And now the hash of account 2 changed.
But what if, but you said it's both sides. So what if account A doesn't want to be public, so he sent 2 nodes to both accounts with $3, but it only contains $3 at first?
Okay. Yeah, that is a very good question, and it's a bit more complicated. Are you familiar with the Zcash model?
Not really.
Okay, so basically every node has a nullifier. So basically how we track nodes in the database is nodes and nullifiers, and you can compute the nullifier, which is a number, like out of the data of the node, you can compute a nullifier, and the nullifier database is just another database where you can see if it's already consumed. So account 1 could send nodes, or could send nodes in theory to a lot of people, the same node, or not even that is possible, but only one could create a verifiable valid proof.
Yes.
Because the operator who verifies these proofs checks, okay, you want to consume this node now, you can do that. Is there already a nullifier or not? If there is a nullifier, you cannot consume it.
Okay, but currently, if I'm wrong, is the nullifier database still under the account 1 state? Or
no, I didn't have time to get to this. Basically, there are 3 different databases how we capture state. So there's an account database, a nodes database, which is an append-only accumulator. That's why you can do parallel stuff. And there's a nullifier database. And for every existing node, there is, the nullifier database is basically a key value map, or some kind of Merkle tree structure. And for every node, there's always, I will find a nullifier that's either 1 or 0. And so, these are two separate databases. And this is, does it make sense?
Yeah,
exactly. And so that's why if the first person who has sent a transaction proof consuming this node can do it, but any other following proof will not be verified anymore. I think I'm over time, right? A little bit? Okay, maybe one more question if there is a question. Cool. Then use Maiden next year. Next week.
Inshallah.